All right, AASL2. Today we're going to be talking about a second derivative. I know, we just got over the first derivative and now there's a second one. You guys, the second derivative is not just a clever name. Like if you start with an original function, so original's here, and then you differentiate it, you get the derivative. Or sometimes this is called the first derivative. If you take the derivative of the derivative, this is called a second derivative. Please notice that the notation here is that you put two little apostrophes on it, so it's f double prime. Now, why would you want to take a second derivative? What does it tell us? That's a great question. We know that this original is a point machine or a coordinate machine. The first derivative is a slope machine. And the second derivative, we're going to talk about it later in the video, but I'll just use the word now. It's a concavity machine. Concavity? I went to the dentist once, got a concavity. Good one, Mr. Jolly. Okay. Let's talk about maxima and minima of the second derivative. If the derivative is equal to 0 and the second derivative of the same point, the same x value, the c, is less than 0, then that means you're dealing with a local maximum at x equals c. If the derivative is equal to 0, which is like a horizontal tangent, and the second derivative is greater than 0, you're dealing with a local minimum. Later on in the video, they talk a little bit more about local versus global, or I will talk about local versus global maximums and minimums. So I thought I'd throw this little diagram in here. So here, any of these horizontal turning points, or stationary points sometimes they're called, these have a derivative of 0, and they're these like turnaround points where the slope changes from either uphill to downhill or downhill to uphill. All of these turning points are either maxima or minima. These little mountains and valleys are called local. So this is a local min, this is a local max, this is a local min as well, and this is another local max. But then if you think about the y values on the whole graph, about what's the tallest it gets and the lowest it gets, like here on the graph, this is where it's biggest, and then here is where it is smallest. So this point up here at the top is also called a global max or global maximum. And then down here, this is the lowest the graph gets, so this is called a global minimum. First up, we're going to do a little algebra. Find the first two derivatives of that. Well, it's set up perfectly for the power equation, or the power rule. So first derivative, we've done a lot of this. Do the old pop and drop, pop the 4 out, multiplies, then drop the x value down. Pop and drop again, 3 comes out in front, drop the x squared down, then we get 6x here, and then the 1 goes away. So that's the first derivative. Now, second derivative, you just do it all again. 24x squared minus 6x plus 6. So this is first derivative, this is the second derivative. As you can see from my primes there, first derivative, second derivative. Now, given this function, find f double prime, or the second derivative of 1. So we're going to take the derivative twice and then plug a 1 into it. Before I can take the derivative, I have to do a little rewrite so I can use my power rule. So this is minus x to the negative 1. So first derivative is negative 32x plus x to the negative 2. Now, instead of moving that negative 2 downstairs like you normally would, we're just going to keep it up there because we need it upstairs to do the second derivative. So then we get negative 32 minus 2x to the negative 3. So the second derivative is negative 32 minus 2 over x cubed. Now we need to plug a 1 into that, because that's what the directions said. So it's negative 32 minus 2 over 1 cubed. 1 is a nice thing to plug in because it kind of all goes away. Or, it doesn't really affect that too. Negative 32 minus 2 is negative 34. Use the second derivative to determine the nature of the turning points. Did something get out of order? I feel like I'm missing something. I feel like something got deleted. Oh, no. Oh, no, it's from up here, you guys. We just talked about it. This says you can use the second derivative to determine if something is a local max or a local min, because if you plug your turning point or your horizontal tangent x value into the second derivative and it's less than 0, it's a max. If you plug it into second derivative and it's bigger than 0, it's a min. So first step, we're going to find the first derivative, which is negative 6x plus 3x squared. Now, that's first derivative. Let's find the, what do we call them? Stationary points, turning points. To find the turning points, those are where you have horizontal tangents. So you set your first derivative equal to 0, and then you solve this. Those both can be factored by a 3x, so then you get negative 2 plus x, and then set both of these equal to 0. You get x is equal to 0 and positive 2. So those are the horizontal tangents, the turning points, but we don't know if those are x values of the tops of mountains or the bottoms of valleys. So we're going to plug into the second derivative to figure out if they're local minimums or local maximums. Second derivative is negative 6 plus 6x. That's just me taking the derivative of the derivative. Yeah, so that goes here. Now I need to take these two x values and plug them in to see what kind of local maximum and minimums they are. So f double prime of 0 is equal to negative 6 plus 6 times 0, which is negative. That means at x equals 0, it is a local maximum. Because if you look back up here, it says if the second derivative is negative, that it is a local max. Now, do we have to find the actual coordinates? No, it's just the nature of the turning point. So x equals 0 is a local max. Then if you plug in the other point, 2, you get negative 6 plus 6 times 2. 12, take away 6 is 6, so this is a positive number, which means that it is a local minimum. So x equals 2 is a local min. All right. A point of inflection is a change in concavity, and I'll explain what concavity means in a second. It happens when your second derivative is equal to 0. So concavity, if you have, let's just go with a basic parabola. even though this parabola has a slope, like a negative slope here and a positive slope here, this whole thing has positive concavity because it's concave up. So it's all about like what direction it opens to, I guess is the way to say that. So this is a graph that's concave up. Now concave down, if I would just use, the parabola again, an upside down parabola would look like this. And even though it has two different slopes going on there, or slopes of tangents, this is concave down. So you can get graphs that, have something like this. And like this section is concave down. Put little arrows on it. So like going down, down. But then right around here, it switches from concave down to concave up. So this inflection point is right here. This is called an inflection point. Also, sometimes the book spells inflection like that, which is kind of fun. Weird flex, but okay. Now, I talked about horizontal tangents being turning points. So when you set the first derivative equal to 0, it finds your turning point. So in my first diagram here, this would be where you would get a first derivative equal to 0, and this is where you get a first derivative equal to 0. And these are definitely turning points. But sometimes you get, and so at those turning points, you would have had a change in the slope. It goes from positive to negative, and then negative to positive. But sometimes you get a situation like this, where you have sort of a chair situation. If you take the first derivative of that function and set it equal to 0, you'll find this point right here, but because there's a horizontal tangent there, but that is not a turning point. It doesn't switch from uphill to downhill. It's going uphill on this side and then uphill again. So we're just going to call this a stationary point. So all stationary points, all turning points are stationary points. So these over here are stationary points as well, but they're turning points. But not every turning point is a stationary, I'm getting it backwards already. Every turning point is a stationary point, but not every stationary point is a turning point. So this guy over here is not a turning point. So that's the whole reason that we do those little sign things where we check the different zones about which direction the derivative's going. Find and classify all points of inflection. So for this one, we're going to take the derivative. Set it equal to 0. Let's go ahead and factor that side. 12x squared, x plus 1. Set those both equal to 0, and you get x is equal to 0 and negative 1. So those are the stationary points, but I don't know if it's like, they're turning points or if they're concave up, concave down, local max, local min. So we're going to test those in the second derivative. Did I solve that right? Hold on a second. When I take the second derivative, we get 36x squared plus 24x. Remember that a point of inflection, so these are turning points. But I guess I didn't actually need to find those because I'm just finding points of inflection. My bad. So we don't need this part. But those would be the turning points if we were asked to classify like turning points. Points of inflection are where it changes concavity. You can figure out where something changes concavity by setting the second derivative equal to 0. Now we're going to factor that. 24 and 36 both have a 12 in common, so we'll pull out a 12x. And then that leaves us with 3x plus 2. So then we get, when you set those both equal to 0, x is equal to 0 and negative 2/3. Also, if they're asking for the coordinates, you could plug these back into the OG function, but then you're going to get some gnarly fractions from that negative 2/3. So I'm going to leave it at, that we know it changes concavity at these points. If you were curious about whether it switches from concave up to concave down or vice versa, you could do a test in the second derivative. So putting negative 2/3 here, 0 here, and then picking numbers from these three zones and plugging them into the second derivative to figure out if it's concave up or concave down. Okay, you guys, I think I want to leave it there. I'll do another video soon with some more finer points, but yeah, good luck on your homework and come and ask me questions.